Hello everyone, we are from Mathematical Method subject group. Today we would like to discuss on the heat conduction through a metal bar. So here goes our discussion.
In this case, consider a thin metal bar of homogeneous material of length L which is placed on x-axis of an xy coordinate system. Thus, the 1D heat equation is given by first derivative of u in terms of t is equals to second derivative of u in terms of x multiplied with k, where k is called the diffusivity of the metal bar. To solve this problem, we assume uxt in this form, where x into x, t into t. These are the boundary conditions for this problem, where x0 is equals to 0 and xl equals to 0, where these are the homogeneous boundary conditions. We derive ODEs for x and t. Derivative of u in terms of x, we will get xt prime and we set as equation 1, and second derivative of u in terms of x, we will get x double prime t and we set this equation into equation 2, and then substitute equation 1 and 2 into the 1D heat equation. After substitute, we will get x t prime equals to constant k x double prime t, and then separate the variables and equal it to a constant. In this case, we let lambda is a constant. So then we have two ODE differential equation where t prime equals to lambda kt and x double prime minus kx equals to 0. Now we need to solve both differential equation. Let's look at the first equation. X double prime minus kx equals to 0. To solve this equation, we need to consider three cases for k. We use the boundary conditions to figure out what values of what values of lambda are eigenvalues. For case 1, we let k equals to lambda square more than 0, where lambda more than 0, and we substitute k equals to lambda square into this equation and let it equals to 0. Our xx equation is a exponential kx plus b exponential negative kx. We let x0 equals to 0 and substitute into this equation, we will get a equals to negative b. And then we let our xl equation equals to 0 and we substitute L into this equation and we will get a equals to 0 and b equals to 0. Hence, there is no non-trivial solution for case 1. Let's go to case 2, where k equals to lambda square equals to 0. Our x double prime is equals to 0, and then x prime equals to a, and let x equals to ax plus c. And when we have x0 equals to 0, and when we solve this equation, we will get b equals to 0. And our x equation is ax. For x, when we let xl equals to 0, we will get al equals to 0 and a equals to 0. Hence, there is no non-trivial solution for case 2. Let's go to case 3, where k equals to negative lambda square less than 0. We substitute k equals to negative lambda square in this equation. Our xx equation equals to a cos lambda x plus b sin lambda x. We let x0 equals to 0, and when we solve this, we will get a equals to 0. And let xl equals to 0, and when we solve this, we will get sin lambda l equals to 0. Hence, there is non-trivial solution for case 3. Thus, the corresponding eigenfunctions for this problem are x and x equals to bn sin lambda and x. As we all know, sin theta equals to 0 and we can conclude that lambda equals to n pi. So, sin n pi equals to 0. Now, we have sin n pi equals to 0 and sin lambda L equals to 0. So, by comparing these two equations, we will get sin lambda L equals to sin n pi. Hence, from this equation, we can conclude that lambda L equals to n pi and lambda equals to n pi over L, where n equals to more than 1. Substitute lambda equals to n pi over L into this x and x equation and we will get x and x equals to bn sin n pi over Lx. Now solve equation 1, which is t prime equals to k lambda t. Let k equals to negative lambda square and substitute into this k, we will get negative lambda square bracket lambda t. And we all know lambda is equals to n pi over L. So substitute into this equation, we will get negative lambda bracket n pi over L multiplied by t. Thus, we will get t equation equals to Cn exponential negative k n pi over L square t, where Cn is a constant and lambda equals to k. Hence, we will get the general solution of uxt equals to b naught over 2 plus summation of bn sin n pi x over L exponential negative k n square x square over L square t. And we let lambda n equals to n pi over L and we will get the final general solution like this. As we all know, ux0 is equals to fx where fx is equals to x. Substitute t equals to 0 into the general solution and we will get ux0 equation is equals to b naught over 2 plus summation bn sin lambda n x. From this, we can conclude that this equation is a Fourier sine integral. Hence, we can form an is equals to 0 and bn is equals to 2 over L integrate fx sine lambda n x, and it is an odd series. Thus, it is proven.
Referring to Appendix 1, let us look at the maple instruction to plot graph for 1C for part 1 till part 4. Assign fx equals to x and set a limit which is set until 5. Later find the sequence of 5 for the integration part using the interval 0 to 1. Then do the summation for the general formula found in 1b. Plot a graph in 2D and also plot a graph in 3D. This is how the graph looks like. Repeat the same thing for the interval 0 to 2 until 0 to 4. For 1C part 5, it is given that fx is equals to x and the interval given is 0 to 0.5. Same goes as from part 1 to part 4. We fix the value of n and we find the sequence for the integration. And we also find the summation for the general formula found in 1b. Then we plot a 2D graph. This is how the graph looks like. And we also plot a 3D graph. This is the graph. Same goes for fx equals to 1 minus x. The interval given is 0.5 to 1. We use the same method. We fix the n value. We find the sequence for the integration. And we also find the summation for the general formula. And we plot a 2D graph, which looks like this, and also a 3D graph, which looks like this.
Is fixed at 0 at the left hand and insulated at the right hand side. We assume uxt is equals to x into x and t into t. And these are the boundary conditions for this problem, where x0 is equals to 0 and x prime L is equals to 0. And these boundary conditions are different from the previous problem where in question 1. This is because the temperature is fixed at 0 at one side and insulated at the another side. We derive ODEs for x and t, where derivative of u in terms of t is equals to xt prime, and we set as equation 1. And then second derivative of u in terms of x is equals to x double prime t, and we set as equation 2. Then substitute equation 1 and equation 2 into the 1D equation. And we will get x t prime equals to constant k x double prime t. Separate the variables and equal it to a constant. And in this case, we let lambda is a constant. So then we have two ODE differential equation where t prime equals to lambda kt and x double prime minus kx equals to 0. Now we need to solve both differential equations. First, solve equation 2. X double prime minus kx equals to 0. To solve this equation, we need to consider three cases for k. But as we all know, this problem is different from the previous problem in 1b because the temperature of one end is 0 and the other end is insulated. So the general solution for this problem is given by this. For case 1, we let k equals to lambda square more than 0. When we substitute k equals to lambda square, we will get this equation. And our xx equation is a cos square root lambda x plus b sin square root lambda x. And our x prime equation is equals to negative a square root lambda sin square root lambda x plus b square root lambda cos square root lambda x. And let x0 equals to 0 and solve this equation. We will get a equals to 0 where cos 0 is not equals to 0. And then let x double prime L equals to 0, and when we solve this equation we will get b square root lambda cos square root lambda L equals to 0 where a equals to 0. To have a non-trivial solution, b is not equals to 0. Therefore, cos square root lambda L is equals to 0. When we move cos into the other side, we will get square root lambda L is equals to 1 over 2 pi. And let this equation equals to equation number 1. On the other side, let x and L equals to 0. When we substitute this equation, we will get sin square root lambda and L equals to sin lambda and L equals to 0. And we all know sine lambda L equals to sine lambda n pi. When we solve this equation, we will get square root lambda L equals to n pi, and let this equation equals to equation number 2. Compare both equation number 1 and 2. By comparing, we will get n pi equals to 1 over 2 pi. When we move this equation, we will get n minus 1 over 2 pi. Now, square root lambda is equals to n minus 1 over 2 pi over L. And this square root we move to other side, we will get n minus 1 over 2 pi over L and square it. Now, our x and x equation is equals to sine lambda x and x. Substitute the this lambda equation into this x and x equation, we will get this equation. And when we summarize this equation, we will get sine n minus 1 over 2 pi over Lx. For case 2, we let k equals to lambda square equals to 0. Our x-x equation is equals to a plus bx. And when we differentiate this equation, we will get x prime x equals to b. Let x0 equal to 0, we will get a equals to 0. And let x prime L equals to 0, and we will get b equals to 0. Hence, lambda square equals to 0, it is not an eigenvalue. For case 3, we let k equals to lambda square less than 0. And for this case, our x-x equation equals to a exponential square root negative lambda x plus b exponential negative square root lambda x. When we differentiate this equation, we will...
Referring to Appendix 2, plotting the graph for 2b using the same method as we used in case 1c. Since in the general solution, it has a variable k in it, it varies according to the interval. It means the k changes and also the interval changes. We assign fx equals to x and we fix our limit. Later we find the sequence of integration part using interval 0 to 1. We also assign k equals to 1 and then we find the summation for the general formula found in 2a. Then we plot our graph. Graph for 3D. This is how it looks like. We repeat the steps for the interval 0 to 2 till 0 to 5 while changing the value of k also. Every time we change the value of k and the interval, we get a different graph. This is for k equals to 2 with the interval of 0 to 2. This is the graph for 4, k equals to 4, and the interval 0 to 4. Next, repeat the steps for the function fx equals to x with the interval x is equals to 0 to 0.5. We find the sequence of integration and we also do the summation. We get this graph. We also repeat the same step for fx equals to 1.
Part C, let's look at the difference between the change of boundary conditions on the metal bar temperature in question 1 and question 2. For question 1, we set the boundary conditions where the temperature of each end of a metal bar is fixed. However, for question 2, the given boundary conditions are one end is fixed and the other end of a metal bar is insulated. That means no heat can flow out of the end is insulated. So, this means that we need to spend extra time dealing with the very end of a metal bar which is insulated. In conclusion, insulated metal bath takes longer time compared to metal bath which have same temperature at both ends.